This video will cover the first part of Section 2 in Chapter 14, where we'll learn how to calculate the simple linear regression model and interpret the slope coefficient. Regression analysis is used to predict the value of a dependent variable y based on the value of at least one independent variable x. It can also be used to explain the impact of the changes in the independent variable on the dependent variable. The rate of change, or the slope, is that impact. The dependent variable is the variable we wish to explain or predict. The independent variable, or variables, are the variables used to explain the dependent variable. In simple linear regression, we have one x, and the relationship between x and y is described as a linear function, a y equals mx plus b type equation. Changes in y are assumed to be caused by changes in x. In multiple linear regression, we use multiple x's to explain the y, and y is a linear function of each of those x's. Again, we assume that the change in y is caused by a change in the x's. So for simple linear regression, our one x variable, y is a linear function of x. Y is the dependent variable. Our population intercept value, our y-intercept value, or the constant in the equation, is beta 0. Notice there's no x variable times that, plus this population slope coefficient beta 1 times x. X is our independent variable. This piece of this, beta 0 plus beta 1x, is called the linear component. Y is a linear function of x. This piece y equals beta 0 plus beta 1x estimates the true relationship between x and y. However, unless y is a perfect linear function of x, the actual y value that we observe will probably not be on the line. The residual, our little curly e here, represents the random component of y that's not explained by this linear component. Here's a picture to help us understand that. The red line represents the linear component of the regression equation. The beta 0 is the intercept, so it's how far up or down from 0 the line is shifted. The beta 1 is the slope of this regression line. So the y equals beta 0 plus beta 1x is the equation of the line. And then the error term is how far away from the line that y value actually is. So we've got some value of x and the observed value of y. The line shows us the predicted value for y, and the difference between the observed value and the predicted value is this residual, or the random error that exists in the data. Since we don't know the true regression equation, we'll have to estimate that. This is what running a regression in Minitab or Excel does for us. It estimates the regression line. So the estimated or predicted equation that helps us understand what's going on with the y is written as y hat equals b0, this is our best guess at what beta 0 is based on our sample of data, plus b1, this is our best guess at what the slope coefficient beta 1 is, again based on our sample of data, times the independent variable. Notice that we do not have an error term here. That's because the error term is about each individual observation, and what we're trying to do here is estimate the linear component of the true regression equation. B0 is the estimated average value of y if x is 0. B1 is the estimated change in the value of y as a result of a 1 unit change in x. So B1 is really read like a slope or a rate of change. So let's walk through an example here. Suppose that you're a real estate agent and you're interested in determining the relationship between selling price and how big a home is. It makes the most sense that the size of the house would determine the price and not vice versa. So our dependent variable is the house price. And the house price is listed here in thousands of dollars. The independent variable then is the square feet. That's the thing we believe determines the price of the home. So in Excel, you can run data analysis regression. I'll show you how to use Minitab in class. We highlight our y variable into the input y range and our x variable into the input x range, check labels, and hit OK. This is the actual Excel output. So the output tells us that the y-intercept is 98.24883. So house price, with the hat on it, because that tells us this is the predicted equation, equals the intercept plus, this is the slope coefficient here, 0.10977 of the variable square feet. So plus that slope coefficient, 0.10977 times square feet. This is a scatter plot of the data and the regression line. The actual regression line that the computer generated is the black line. The red dashed lines just extend that line so that you can see the estimated regression equation that the computer generates for us. The intercept is 98.248, so the red line extends down to that 98.248. And the slope of this line is 0.10977. When using this equation to predict, we really only can make predictions inside the range of the data, inside the black line. Any prediction outside of that, any prediction on the red dashed lines, is less likely to be accurate. Let's talk about each of these coefficients that the computer generated for us. The B0, or the 98.248, tells us what? Well, since there's no houses that have 0 square feet, that 98.24833 really just tells us that $98,248.33 is the portion of the house price that's not explained by square feet. So this could have to do with the land value, it could have to do with amenities that are in the home, all of those kinds of things. B1, or our slope coefficient, is 0.10977. What that actually tells us is that for a 1 square foot increase in the size of the home, we expect the house price to go up by $1,0977,000. Or you can say it this way, we'd expect the average value of a house to increase by $109.77 for each additional 1 square foot in size. This will look a lot like what we saw when we were doing the ANOVA, the sum of squares total. That's all the variation in y about the mean. So y minus y bar squared, we sum all of that up. We find out how much total variation there is in our y variable. The sum of squares regression is really how much of the variation in y is attributable to the relationship between the y and the x or x's in the equation. Our y hat is the predicted values of y. So this is how far away the predicted value of y is from the mean. We square that and sum those all together to get the sum of squares regression. The sum of square error. This is all the variation in y that is not explained by the regression model. So the variation in y that's not attributable to the relationship between the y variable and the x variables that are included. To calculate this, we take the y value minus the predicted value, square that, and add up all of those values. To see this in a picture, the y bar is represented by the green line across the page. The predicted value of y is the red line that has the y hat on it. The sum of square total is how far away from the average the individual data point is. This yi, or our blue dot up here, is the actual data value. The sum of squares total is how far away from the green line, or the average of y, this value happens to be. So you'll see the sum of square total here is the total difference between these values squared and added them all together. The sum of squares regression is the distance between the yi and y bar that's actually explained by the regression equation. So at this value of x, the y hat here explains this much of our variation in the y value. There's a part of this then that's not explained by the regression equation, or the error part. The distance between the regression line and the data point, or this piece over here, is the unexplained or sum of square error part of the regression analysis. What we'd like to see is that our regression model explains a significant portion of the variation in our y value. The numerical measure we use to talk about this is the coefficient of determination. The coefficient of determination is the proportion of the total variation, so sum of squares total, that is explained by the regression equation. So we put sum of squares regression on the top, divided by the sum of squares total, and that tells us the proportion of the total that's explained by the regression. This value will always be between 0 and 1. In cases where you only have one independent variable, it is the case that r squared, or the coefficient of determination, is actually the same as the simple correlation coefficient squared. To provide a visual of the relationship between x and y and r squared values that we might get from our regression output, I provided a few graphs here. So the first two graphs here, the left-hand column, shows us an r squared of 1, which means x perfectly predicts y. In the first case, there's a negative relationship between x and y. In the second case, there's a positive relationship between x and y. But all the variation in y can be perfectly predicted by the variation in x. In the center column, we have an r-squared value being between 0 and 1. The top picture shows x increasing and y pretty much decreasing. They don't move perfectly together. The bottom picture shows an r-squared that would be closer to 0 than the top picture. X increases, we see y increase, but the relationship between x and y is looser. The dots are further away from the line. The regression equation is not explaining as much of the variation in y. If we get an r-squared of 0, which we theoretically can get, we usually don't get in practice, what that means is the movement that's happening in x has no explanatory value with what's happening in y. Because of spurious correlation, though, we usually do not get an r-squared that's 0. So again, let's look at our Excel output from our housing prices and square feet example. The r-squared is actually generated for us. The computer has taken the ANOVA values here from the regression and total, sum of squares, divided those for us, and provided us with the r-squared value up at the top of the output. R-squared is 0.5808. What that actually tells us is that about 58% of the variation in house prices is explained by the variation in square feet. So square feet is relatively important in telling us how expensive house prices will be. The next video will talk about hypothesis tests and also using the estimated regression equation for prediction purposes.